and of course our today's award winner, Professor Helmut Schwarz, Emeritus of the Technical University of Berlin. I want to also welcome Professor Sophia Becker, the Vice President of the TU Berlin, who will give a welcome address in a minute. It is also my pleasure to welcome our colleagues and supporters from BASF, the chemical company, Dr. Detlef Kratz and Frank Rosowski from Baskat. And last not least, I'm glad to have our colleagues Joachim Sauer, Matthias Tries, and Eckhard Rühl here, who are the representatives of the Humboldt University, the Technical University, and the Freie University for the Gerhard Ertl Lecture. So, welcome to all of you, ladies and gentlemen. We want to celebrate the Gerhard Ertl Lecture. I'm Martin Wolf, and I'm currently the Managing Director of the Fritz-Haber-Institut. As such, I have the pleasure to guide you through the program. Gerhard Ertl was awarded the Nobel Prize in a ceremony which took place almost exactly 16 years ago on December 10th, 2007. At this time, the chemistry community in Berlin felt that it would be a good idea to install a special prize, the Gerhard Ertl Lecture Award, which is awarded by all three Berlin universities, the BASF, the Fritz-Haber-Institut. Gerhard Ertl kindly accepted this proposition, and in December 2008, 1 year after his Nobel lecture in Stockholm, the first awardee, Gabor Samachai, was delivering the first Gerhard Ertl lecture. Since then, the series continued with numerous excellent and well-known awardees from all over the world. Today, it is a great pleasure to honor another renowned scientist and esteemed colleague, Professor Helmut Schwarz from Berlin. This award is made possible by the generous support from BASF. Chemistry research in Berlin, in particular in catalysis, is significantly supported by BASF, including the joint laboratory Baskat. On behalf of the scientific community and the audience, I would like to thank BASF for this support. Let me also thank Daria Haberland, Sabine Frebel, Jelena Tomovic, and Carsten Baldauf for their great help to prepare this event. The program is now as follows. First, Sophia Becker will give a welcoming speech as Vice President of the Technical University Berlin. After that, we will hear the Laudatio delivered by Detlef Kratz from BASF. This is then followed by Helmut Schwarz, who gives a lecture entitled The Methane Challenge, a cold approach to a hot problem. After this lecture, a certificate and a special book will be handed over to Helmut Schwarz. And then there will be a reception where everyone is welcome, also to shake hands, to discuss and have a drink with the award winner. Thank you for your attention.
Okay. Yeah, ladies and gentlemen, dear Professor Schwarz, dear guests, I actually prepared my little speech in German, and so I hope that most of you can follow, because I think it will be too hard to translate it from spontaneously from one minute to the other. And also I have included some citations from Goethe, so I hope you can enjoy those in German. Ja, meine Damen und Herren, wir sind heute hier im Goethe-Saal zusammengekommen und deswegen möchte ich Sie auch mit seinen Worten begrüßen. Willst du dich am Ganzen erquicken, so musst du das Ganze im Kleinsten erblicken. Goethe hat diese Zeilen in einem pantheistischen Sinne formuliert. Sie passen aber vielleicht auch ganz gut auf die Massenspektrometrie, bei der man das Ganze im Kleinsten erblicken kann. Und damit sind wir natürlich beim eigentlichen Thema des heutigen Abends. Wir haben uns heute hier eingefunden an diesem geschichtsträchtigen Ort, dem Harnack-Haus im Goethe-Saal, um gemeinsam unseren Kollegen Professor Helmut Schwarz zu ehren. Denn, das wissen Sie alle, Ihnen, lieber Herr Schwarz, wird heute ein Preis verliehen, der Gerhard Ertl Lecture Award. Und darüber freuen wir uns als Präsidium der Technischen Universität Berlin natürlich ganz besonders und fühlen uns auch als Ihre Alma Mater ein wenig mit geehrt. Ich hoffe, das ist in Ordnung. Denn wenn ich so rückblicke auf die letzten Jahrzehnte, die ich zwar nicht selber miterlebt habe, aber es gibt ja verschiedene Informationsquellen, dann sieht man doch, Helmut Schwarz und die Technische Universität Berlin, das ist eine Freundschaft fürs Leben, ist mein Eindruck gewesen. Und dafür danken wir Ihnen ganz herzlich für Ihre Treue in diesen vielen Jahrzehnten, denn wir wissen, dass Sie auch viele andere Angebote hatten, aber Sie sind der TU Berlin treu geblieben. Sie haben mehr als ein halbes Jahrhundert lang Ihre Forschung an der TU Berlin betrieben und damit auch die Chemie und die Forschung zur Chemie an der TU Berlin sehr geprägt. Dass wir als TU Berlin mit dem Exzellenzcluster zum Thema Katalyse bisher zweimal erfolgreich waren und nun auch die Antragsvorbereitungen für die nächste Runde auf Hochtouren laufen, das ist natürlich immer die Arbeit und auch der Erfolg eines großen Teams. Aber ich glaube, dass es nicht übertrieben ist zu sagen, dass Sie mit Ihren Forschungsarbeiten und Ihrem großen persönlichen Engagement einen wesentlichen Grundstein dazu gelegt haben, von dem wir noch heute zehren. Aber, lieber Herr Schwarz, Sie waren nicht nur an der TU Berlin und in der Grundlagenforschung wirkmächtig, sondern Sie haben auch hohe Führungspositionen in wissenschaftlichen Gremien und wissenschaftspolitischen Organisationen innegehabt. Es sind zu viele, um sie hier alle aufzuzählen, aber ich greife mal das Präsidium der Leopoldina und die Zeit als Präsident der Alexander von Humboldt Stiftung heraus. Ja, Führung, das heißt Verantwortung, und die haben Sie sehr freudig übernommen, wie es mir scheint. Führung heißt auch Macht. Und Macht ist gesellschaftlich doch oft etwas negativ konnotiert. Und da kommt bei mir die Sozialwissenschaftlerin und Soziologin durch, und ich halte es mit Hannah Arendt und ihrer positiv konnotierten Konzeptualisierung von Macht. Ich zitiere: Macht entspringt der menschlichen Fähigkeit, nicht nur zu handeln oder etwas zu tun, sondern sich mit anderen zusammenzuschließen und im Einvernehmen mit ihnen zu handeln. Oder wie Jürgen Habermas diesen Arendtschen Machtbegriff interpretiert, Zitat: Das Grundphänomen der Macht ist nicht die Instrumentalisierung eines fremden Willens für eigene Zwecke, sondern die Formierung eines gemeinsamen Willens in einer auf Verständigung gerichteten Kommunikation. Führung ist Verantwortung, Führung ist Macht, Führung ist Gestaltung. Sie haben Ihre Führungspositionen im positiven Sinne als gemeinsame Gestaltungsmacht verstanden. Und deswegen freue ich mich, dass wir Sie heute Abend nicht nur als herausragenden Wissenschaftler, das wäre schon Ehrung genug, sondern auch als inspirierende Führungspersönlichkeit ehren. Und bevor wir gleich die Laudatio hören, möchte ich mit den Worten des großen Dichters und Denkers schließen. Alles kommt in der Wissenschaft auf das an, was man ein Aperçu nennt. Auf ein Gewahrwerden dessen, was eigentlich den Erscheinungen zugrunde liegt. Und ein solches Gewahrwerden ist bis ins Unendliche fruchtbar. Vielen Dank und herzlichen Glückwunsch, lieber Herr Schwarz.
So, back to English. Dear Professor Schwarz, dear Professor Ertl, online, dear Sophia, dear Martin, ladies and gentlemen, and of course everyone who is listening in. What a great pleasure, an honor for me to introduce this year's winner of the Gerhard Ertl Lecture Award, Helmut Schwarz. We already heard, distinguished professor of organic chemistry at TU Berlin until 2022, former president of the Alexander von Humboldt Foundation, member of the Presidium of the Leopoldina National Academy of Sciences, and vice president of the German Research Foundation. With these titles, Helmut, what more do I need to say? I could stop the Laudatio here. But one moment, there is, of course, the Gerhard Ertl Lecture Award. So there's more. The committee has selected you for your pioneering work towards reaction mechanisms via mass spectrometric techniques. And these studies shaped our understanding of elementary processes involved in catalysis, in organic metallic bond activation and functionalization, and what is more important than ever, in atmospheric chemistry. Ladies and gentlemen, before we dive deeper into the accomplishments of our esteemed awardee, let me just say a few words about the history of the award. Martin has already alluded to this. In 2008, the Gerhard Ertl Lecture Award was established and presented for the first time, and that by several renowned institutions. First, by 3 Berlin universities. Second, by the Fritz-Haber-Institut. Third, by UNICAT. And fourth, by BASF. The intention was to express deepest appreciation for one of the most prominent scientists in the field of catalysis, who was awarded the Nobel Prize in Chemistry in 2007. You, dear Professor Ertl, listening in. Well, this prize tonight is awarded for the 16th time. It is highly regarded in the scientific world, and the impressive list of previous award winners, we are talking about outstanding personalities and distinguished researchers in the field of catalysis, shows this very clearly. It also shows strong partnership between academia and industry, and that is our partnership. And here in this audience, I don't have to emphasize the role of catalysis in terms of importance and effectiveness in chemical processes. But let me just add that for BASF, catalysis has played a crucial role since we developed the ammonia synthesis and its catalyst in cooperation with the University of Karlsruhe more than 100 years ago. And it's throughout the history of our company that collaboration with academic partners has always contributed significantly to our research activities and to our success. And we have remained true to this spirit in cooperation and therefore founded BASCAT at the TU Berlin in 2011. That's also more than 10 years ago, a laboratory jointly operated by UNICAT and BASF. That is a success story for us. But back to the present. And the most important topic of tonight, let me introduce this year's awardee in more detail. Helmut was initially trained as a chemical laboratory technician and studied chemistry with a scholarship of the German National Academic Foundation. And he obtained his diploma in 1971 with first-class honors, completed his doctorate in 1972 with first-class honors, and achieved his habilitation in 1974. What a speed. It looks like you, Helmut, are not only extremely smart, but also on the fast track. After research stays at MIT, at ETH in Zurich, and Cambridge University, that's quite an impressive list, if I may say so, he became a professor at the TU Berlin in 1978, leading the Department of Chemistry, to which he devoted his further academic career. And Sophia, you already mentioned it, and that with all his heart. Numerous national and international awards pave Helmut's career path, including 10 honorary doctorates, and they all reflect his exceptional scientific expertise. And if I would mention all accolades, we would run out of time. So let me just mention one or two of them. In 2003, for example, you received the Otto Hahn Award for Chemistry and Physics of the German Chemical and Physical Society. And on this occasion, it was Professor Ertl who described Helmut in his laudation already, and I quote, as the Mozart of contemporary gas-phase catalysis. Wow. I mean, we already heard Goethe, but Mozart, what more can I say? And he nicely pointed out Helmut's central role in reshaping mass spectrometry and gas-phase chemistry. That was an early pinnacle. Then there was the Order of Merit of the Federal Republic of Germany, or in German, das Bundesverdienstkreuz erster Klasse. And that was awarded to you, Helmut, in 2012. And 3 years later, you received the Karl Ziegler Prize, and in 2021, the Leonardo da Vinci Award of the European Academy of Science. Apart from your pace-setting research, our awardee has been deeply committed to strengthening academic institutions in Germany and beyond, whether as co-founder of the Berlin-Brandenburgische Akademie der Wissenschaften, as vice president of the German Science Foundation, or as president of the Humboldt Foundation, to name just a few. But more important, most impressive is your research, Helmut. You are considered one of the world's leading researchers in the field of molecular chemistry. You are an expert in organometallic chemistry, particularly in the selective activation of bonds in organic molecules by transition metals in the gas phase. Your fascinating research has tremendously improved the understanding of catalytic processes and has driven the development of tailored catalysts, which is, of course, also extremely interesting for companies like BASF. As a true trailblazer, you also played a significant role in advancing mass spectrometry. The Schwarz Group at the TU Berlin contributed a lot of pioneering work to this field, focusing on the last decades on the selective activation of inert CH bonds. In particular, it concentrated on methane, and that for good reason, namely the environmentally beneficial conversion of hydrocarbons into value-added products. And I guess we will be hearing more of that in your lecture later on. Your publication list is outstanding, and it covers an enormous range of topics. Overall, your track record encompasses more than 1,000 research articles in peer-reviewed journals and also 1,000 named and invited lectures. You are worldwide one of the most often quoted mass spectrometrists and among the top-cited chemists overall, with an H index of 89. Truly impressive, but it's not all about numbers. I think even more important is that you were a great mentor to many, many master and PhD students and postdocs. As a Spiritus Rector, you followed the so-called Harnack principle. You not only gave them the most possible support, but also the most possible amount of freedom. You encouraged and enabled them to perform at their best. You gave them the feeling to be part of an extraordinary group and inspired them. It is well known that the seminars within the Schwarz Group were really special, illustrious, and often enriched by international top scientists. No wonder that the output of your research group was so amazing. And talking about internationality, you're not only a great scientist, but also a statesman. As president of the Humboldt Foundation, you also followed Humboldt's ideal, the strong connection between research and teaching. And it's one country that was especially close to your heart. And in these days, it is particularly important to mention, and that is Israel. Since your first visit in 1978, you fell in love with Israel and its scientific community. More than 120 visits followed, and you excited professors and students about your research. And the result? Many collaborations and wonderful friendships. Considering all that, it seemed that you lived several lives. Looking at all your activities, one could think you only cared for science. But the opposite is true. Your claim to excellence in life is a holistic one. You are very interested in many other intellectual activities, like enjoying theater, the opera, and literature. People like you, Helmut, polymaths, probably don't need to sleep a lot. Dear Helmut, I hope I made it clear the global scientific community would be so much poorer without you. My heartfelt congratulations on your lifetime's achievements and, of course, today's award. And without further ado, we are looking forward, of course, to your lecture. The Methane Challenge, a cold approach to a hot problem. Thank you very much.
Well, after this extremely friendly words of welcome and the exceedingly kind Laudatio, I'm afraid it will be a very, very great challenge to live up to the expectation you have raised with your words. But I will try hard. Can I have the first slide, please? The first slide, please. There we are. Kurt Mislow's remark on basic research and its relationship to the arts could well have served also as a leitmotif for Gerhard Ertl. For example, in Gerhard's fundamental work on surface chemistry, he came across the observation of spirals, of two-dimensional waves. And those of you who are a little bit knowledgeable about the work of Leonardo da Vinci, they do see immediately the close correspondence between art and sciences. But moreover, Gerhard Ertl, there's a problem. Gerhard Ertl is not only an eminent scientist, he is also an accomplished musician, as we see here, a man of broad interest, a real intellectual, but above all, he is a great friend, a unique friend. And therefore, it is more than a privilege to have been invited to deliver today's Gerhard Ertl lecture, in which I will talk about this topic on methane. Why methane? Simple molecules like methane and carbon dioxide continue to make headlines for various reasons. Each year, roughly 10 to the 9 metric tons of methane are released to the atmosphere, where methane acts as one of the most potent greenhouse gases. And a similarly large amount of methane is flared to produce another greenhouse gas, carbon dioxide. And so the question is there no better use of this precious feedstock to valorize methane and to convert it to something more valuable? Well, in fact, any idea to convert methane to another chemical has to start with activation of a CH bond. And when you look at the structure of methane, it is quite clear, is there a problem at all? There are 4 identical bonds, no stereochemical requirements, no regiochemical requirements. So what is so special about it? However, since the work of Bergman in Science in 1984, in this 40 years, more than 17,000 scientific articles have been published dealing with one or the other aspect of methane activation. 17,000 articles. But despite this enormous industrial and academic interest in this topic, there are still problems. For the time being, we have no idea to bring about in an environmentally benign, economically viable way, the large-scale room temperature conversion of, for example, methane to methanol, or for example, the coupling of methane and carbon dioxide to generate acetic acid, or the direct production of H2O2 of ammonia. We really don't know how to do that. Of course, part of the problem why this cannot be achieved is due to the fact that for methane activation, there are some intrinsic features which prevent us. There's a problem. It does not move on. What can I do in order to... Can anybody help me? I would like to have the next slide. Aha, good. But we are at the Fritz-Haber-Institut. We are supposed it goes faster. So, there are some intrinsic properties. For example, methane has, among all saturated hydrocarbons, the largest CH bond. Moreover, the ionization potential, as shown here, is very large. The electron affinity is negative, so any kind of redox processes, they don't work. What about acid-base type chemistry? The proton affinity is also not substantial compared with water, for example, not to speak of ammonia. And the acidity of methane is such that, for example, Coca-Cola in comparison with methane, Coca-Cola is a superacid. So, what can we do? What can we do to bring about methane activation? When we embarked on this scientific journey in the late 80s of the last century, we were guided by Max Planck's dictum from 1919, knowledge ought to precede application. And moreover, we also did not try to come up with any kind of recipes. Rather, we wanted to develop concepts aimed at an understanding at a truly molecular level. What are the elementary steps to activate such a simple molecule? And to do that also in a way which is not obscured by any kind of ill-defined effects like solvents effect, aggregation effect, and all this kind which makes chemistry so difficult. In our attempts to understand a little bit better why it is so difficult to activate methane, there were three areas in which we tried to make some contribution. The first one was the direct conversion of methane in a metal-mediated way to produce metal carbines. And it turned out that that is an area in which very, very strong relativistic effects matters. Only those elements, for example, like platinum, which do have this kind of effect, they are capable to activate the strong CH bond of methane and to form metal-carbon multiple bonds. The second topic of interest is this direct conversion of methane to methanol, which in the view of Nobel laureate Sir Derek Barton is one of the many holy grails in chemistry. And it turned out that this metal oxide mediated oxidation of methane to methanol is a reaction, in which at room temperature or under thermal condition, not only one state is involved, but various states are involved. And that was a project which we worked on in collaboration with Sasson Shaikh from the Hebrew University. And we learned that this kind of two-state reactivity paradigm is a system which does not only hold true with this kind of chemistry I've shown here for simple metal oxide, but it has also helped to resolve decade-long discussions in the metal community, because metalloenzymes are also the species which in nature, for example, bring about this kind of chemistry. And the third reaction is this reaction shown below, the oxidative coupling of methane. Another dream reaction to convert methane, for example, to C2H4. This process here is, of course, also an example of the ubiquitous hydrogen atom transfer chemistry on which I will spend the next 20, 30 minutes or so before switching gears. There's an interesting bimodal distribution for the activity in the oxidative coupling of methane. There was a huge interest in the 90s, and then it faded away. And later on, in more recent years, there is again much more interest to understand this kind of chemistry. Part of the early interest can be traced back to a mechanism which was suggested by Lunsford in the 80s, so last century. And according to Lunsford, the reaction is as follows. When magnesium oxide is doped with lithium, at high temperature, some species are generated which contain, as shown here, oxyl sites here. Nein, Sie dürfen nicht weitergehen. Oder wir zeigen die Deal, ich sage nichts. Ja, das können wir auch.
Ich würde gerne diese Titelzeile loswerden.
Stört die einen?
Ja. Also schön ist es halt nicht.
Wir wollen ja was lernen, nicht nur Schönheitswettbewerb. Ja.
Aber ich weiß nicht, wo das.
Also wollen wir lieber zurückgehen wieder. Wollen wir mal sehen. Right. So, Lunsford suggested that when magnesium oxide is doped with lithium, oxyl species, these are species where the oxygen atom there is a radical side, are generated. And that is the species which brings about homolytic cleavage of the CH bond. But even at that time, there were already some criticism, and people were not really happy about it. In fact, based on a very detailed statistical analysis, in which close to 2,700 articles were reviewed, more than 140 patents were carefully studied, and close to 1,900 different set of catalysts were investigated. It was concluded, you can read it by yourself, the real structure, the active sites are unknown. That was the knowledge around 2011. But 3 years later, in a superb article published in collaboration of people from the Fritz-Haber-Institute at Joachim Sauer, they came up with truly unprecedented reaction for a reaction on magnesium oxide. And that is not the conventional homolytic cleavage, because this reaction is usually characterized by a relatively small barrier. But the experimental barrier is of the order of 90 to 100 kilojoule per mole. And what is suggested is shown here. It is, as I mentioned, an unprecedented process in which a magnesium carbon bond, a Grignard type chemistry takes place. I will come back to that later, because that is one of the very, very rare examples in which proton-coupled electron transfer, which is so typical in everything in enzymatic processes, also seems to hold true here. But the question then still is, what is the situation if we are able to generate cluster oxides, having an oxyl site? Can we make this species not together with the surface, but as free species? And what properties do they have? What do we learn from this kind of chemistry? And therefore, we decided to use our gas phase approach to make this cluster oxide, to isolate them, to characterize them, I will come to that in a minute, and then to study them under very well-defined conditions to see what are the elementary steps. But of course, the first question is, what are we talking about? How do these clusters really look like? What are the active sites in it? In order to do that, we joined forces with Knut Asmis from the Fritz-Haber-Institut and also from Leipzig University by doing action spectroscopy. When light interacts with molecules, all kinds of things can happen. The light can be attenuated, but that is not the case in our system because the number density is so small. Typically, we are dealing with a few thousand molecules at most. So there's no way to extract any kind of useful information from it. But there's an alternative, and that is to turn the question around and to ask, what is light doing to a molecule? What is happening, for example, when a messenger, a noble gas, is added to our cluster oxide? And each time when light is absorbed and the absorbed energy exceeds the bond energy of this helium atom of our messenger to the cluster oxide, the helium will be detached, and that, of course, can then be measured very accurately by means of mass spectrometry. And that is actually what we are doing here by using the free electron laser of the Fritz-Haber-Institute here. And that is a slide I also got from Knut Asmis, in which it is shown that we make our cluster, in our cluster source, we make our oxides, we mass select them, and after mass selection, they are then bent around. We trap them in a cold iron trap at temperature between 4 and 10 Kelvin or so. There we can also thermalize them. We form the complexes, and after a time delay, they are extracted and they are hit with a laser light from the free electron laser, and the product are then detected mass spectrometrically. Of course, the proof is in the eating of the pudding. Does it work? And here we are. That is the experimentally observed infrared spectrum of a celebrated vanadium phosphorus oxide to which 1 or 2 helium are added. And we see immediately, well, there's no big difference between the two. But when we compare the experimentally observed spectrum with spectra calculated for different isomers, here we see immediately that many of them can exclude it. And it is only this rhombus-like structure which is a nearly perfect match. So by this technique, this action spectroscopy, we can really determine the structure. We do know what we are talking about. And for the remaining time, believe me, that is what we have done for most of our experiments here. I should also mention in passing, this technique also enables to address a problem which for the first time was addressed more than 100 years ago by Schwab and by Taylor. That is the question, what are the aristocratic atoms, the active site in an enzyme? For example, is it this part here, is it this oxygen atom or this oxygen atom here, which, for example, in oxidation type chemistry are removed? All this can be perfectly addressed. So, now we know what we are talking about. And the question is, what are the mechanisms? And here we have to distinguish between at least 2, if not more, different variants. The conventional one is this homolytic cleavage, in which just the CH bond is symmetrically cleaved. But another one, to which I will come later, is this heterolytic cleavage, the Sauer mechanism with Grignard type intermediates when we talk about magnesium species here. For the conventional homolytic cleavage, there are also 2 variants. And one variant is a so-called direct pathway. That is a pathway which is typical for oxygen-rich clusters having high oxidation state. There are no vacant sites to which, for example, the incoming methane can be attached. They are characterized by rather small isotope effect, and they include all this kind of oxides here. And the very first example was an example which was studied well more than 20 years ago, vanadium oxide, V4O10. At room temperature, when this V4O10 molecule hits a methane molecule with an efficiency of 60% of the collision rate, a hydrogen atom is pulled away, or in the case of the labeled deuterium atom. Interestingly, the isotope effects are similar for both the vanadium oxide mediated one as well as the one in which just hydroxyl radical reacts with methane. Theory provides some further detail. In collaboration with Joachim Sauer, we did some MD calculation, and from the sheer observation that there is a continuous decrease of the potential energy surface, that is already a clear indication that there are no intrinsic barrier along the reaction coordinate. And moreover, we observe this typical shortening of the vanadium carbon bond when the methane comes closer to the active site here. But roughly after around 450, 500 femtosecond, there's an oscillation. The hydrogen atom jumps between the carbon and the O atom here. But because of the fact that all the energy, we are in a gas phase experiment, that all this energy is by and large vibrationally available. There is no heat mass to dissipate the energy. The system simply flies over it and there is a process in which there are no intrinsic barrier involved at all. So that is just one example of the so-called direct pathway. The situation is completely different when one deals with systems which have awakened metal side. And these are then the so-called metal-mediated CH bond activation. And here we have examples, often small systems, which have not an excess of O atoms here, like the biologically relevant iron oxide, copper oxide, and also magnesium oxide, as we'll see in a minute. In work done by Jana and the late Detlef Schröder, also more than 20 years ago, they observed, again at room temperature, not at 800 centigrade, at room temperature, magnesium oxide in this oxidized state here is capable to pull away a hydrogen atom practically spontaneously. But the mechanism is at least based on very, very detailed, in that case, high-level calculation. It's completely different. What do we observe according to theory here? All the many trajectories, by and large, more than 98% or so, end up by attracting the methane molecule towards the metal side here, where it's also most of the charge. But that is not the active site. The active site is actually at the O atom here, where we have this high spin density here. And then in a metal-mediated fashion, over this submerged barrier, the metal coordinates or relocates the methane molecule to the O side, where the activation occurs, the methyl group is pulled back, and then in an entropically driven, thermochemically unfavored reaction, you are really slow at the Fritz Haber. Really slow. What is the matter? That's not too bad, Martin. Oh. Wollen wir eine Pause einlegen? Oh, das, oh, there we are. Good. Right. So, as I mentioned, in an entropically favored reaction, the methyl group is kicked off because there is this huge excess energy, and the alternative reaction, the thermochemically more favorably bound mechanism, has no chance to compete. So far, I talked about systems which are characterized by the presence of radical doublet states. And the question we were interested in, other people also were interested in, was, is the presence of a doublet state not only the necessary, but also a sufficient condition? As you will see, that is not the case. Because when we compare, for example, magnesium oxide with oligomeric species, the radical cations of the dimer, trimer, tetramer, in contrast to this one does not react at all with methane. They are completely unreactive. Why is it so? The answer is relatively simple. In contrast to diatomic magnesium oxide, where the spin is practically completely at the O side, here the spin is distributed over two bridging atoms. When the system comes together with methane, well, we form an encounter complex, which is highly excited. But this intra-complex spin transfer, which is necessary to reach the transition state, having a high spin density, that is so energy demanding that the reaction cannot overcome the barrier here, except one would external energy pump into it. But with the energy we gain here, no reaction can take place. With other words, spin localization is necessary. If the spin is delocalized, the system has no chance to take place at ambient condition here. How can we mitigate the situation? And the best way is to dope the system, to add to the system some elements, atoms or small molecules, which help to locate the spin at one site here. And that is the case, for example, when oligomeric magnesium oxides are added with BF3 or as shown here with gallium oxide. The complex or the cluster gallium oxide, magnesium oxide, out of a sudden reacts with methane at room temperature. And there's the answer. The reason is that by adding this element here, the gallium oxide shown in red and in purple here, the spin which was delocalized here is now with more than 95% at one side here. And whenever the methane hits this side here, homolytic cleavage occurs. So, doping is excellent. When we published this result, it was met with criticism. It was met with criticism by people of highest reputation, for example, by Jim Meyer. Jim Meyer is one of the world experts also in CH bond activation. He has published hundreds of excellent papers, but mostly papers in which the CH bonds to be activated were weak bonds, benzylic bonds, allylic bonds, and the like. And he concluded that based on his experiment, just by using thermodynamic criteria and applying the Bell-Evans-Polanyi principle developed here in Berlin in the last century, that this is more than sufficient to explain also the kinetic behavior. And so he stated, the presence of unpaired spin density and so on and so forth is not a requirement, nor is it a predictor of any kind of HAT activity. That was difficult for us to swallow. And here are a few examples which clearly show that that certainly does not, this generalized version of Meyer's article in the accounts is certainly not the right way to describe chemistry with methane. Because when we look, for example, at molybdenum dioxide, titanium, zirconium, they do not react. If forever we remove an electron and we make an oxyl site here, at room temperature we get chemistry. Critics may say that is cheating, because here we have a charge, and maybe the charge which does all the chemistry, and not so much the celebrated oxyl site here. But that is not true. Here's the opposite. Here it is the neutral one which reacts with methane, while the charged one, which is a closed cell, a singlet system, does not react at all. And we have many, many more examples which clearly demonstrate that oxygen-centered radicals do indeed matter. The perhaps most convincing examples were provided by looking at aluminum clusters. And there is a clear distinction between two categories. Those aluminum clusters which have an odd number of aluminum atoms, as the one shown here, 5, 7, 9, 11, and so on, they do not react with methane. While those having an even number, 4, 6, 8, 10, they do react. Can we explain that? The answer is relatively simple. They have a few things in common, but the fundamental difference is that for all the clusters having an even number of aluminum atoms, they have in common an oxyl site here. And that, of course, is then the situation in which whenever in the trajectory a methane molecule comes close to that site here, in this barrier-free process, the hydrogen atom is pulled away. In contrast, for the one aluminum 7, although the reaction is exothermic, there's again this intrinsic barrier, this impediment. One has to pay a penalty to build up high spin density. In this system here, the spins are distributed as a triplet ground state over various bridging O atoms here. And all this were most recently also corroborated by an elegant paper by Joachim Sauer, Laura Gagliardi, and Knut Asmis. They looked at clusters, for example, the cluster aluminum 3O4 is completely unreactive. That is this one here. However, when aluminum is replaced by one iron atom, there's a complete structural reorganization and an oxyl site is generated. All that is based on multi-reference calculation, on also using the free electron laser to do spectroscopy. So it's absolutely clear that is a system which has also the potential of bringing about this kind of CH bond activation. So far, I have completely neglected the role of charges. And most likely, charges do matter a little bit, but not really substantially with regard to the very last step. But initially, the charge does matter. What does it mean? When we compare isostructural, isoelectronic system, the difference is in ILO4, vanadium, or we have titanium and we have scandium. The upper one, this one here, is clearly reactive, while the lower one are not reactive at all. And the reason is that for the negatively charged one, the scandium atom here, the whole surface is negatively charged. With other words, when the electron-rich methane approaches it, it feels a repulsive force. And this repulsive force, what is it doing? It repels the methane molecule. With other words, at the entrance channel, there is a barrier which prevents the system from reacting. And therefore, the statement, each atom counts in cluster chemistry, is absolutely warranted. I think that is without power. The laser pointer does no longer work. In any case, we will continue. Let's now change gears and talk a little bit about a completely different process. In fact, the process I mentioned when I mentioned the work of Joachim Sauer. And that is the reaction of small clusters like Al2O2. They also react with methane, but they do it in a completely different way. And this system here, as shown above, is a spin delocalized over two aluminum centers here. So what happens when the methane molecule is added to the aluminum side? Can it bring about activation of the spin here? No, it can't, because for thermochemical reason, an aluminum hydrogen bond is so weak that there is no way whatsoever to cleave the very strong CH bond here. With other words, that would take us in the next floor of the Harnack house here. What is about the conventional HET transfer? That is the one shown in blue. We can make the encounter complex, but there is once more this impediment. That is, there is no spin density at the accepting O atom here, and therefore no conventional HET transfer can take place. But there is a new process, and that is this process here, a multi-centered reaction in which the proton of the CH bond from methane is located to the bridging O atom here, and the electron pair from that bond, disguised as a CH3 minus, is relocated to the Lewis acidic site here. Proton-coupled electron transfer, which many people believed is something which takes place only in biological processes, or as Joachim Sauer has suggested or has shown a couple of years ago in some surface-controlled reaction here. That is one of the first gas phase examples which clearly demonstrate proton-coupled electron transfer is also viable in these systems here. Well, what happens when we have a slightly more complex system? For example, a complex which consists of, shown in green, at the bottom line, magnesium oxides, the dimer, and on the top floor, Al2O3. And that is a system in which now, for the first time, both HAT, because of the oxyl site here, and proton-coupled electron transfer do compete with each other. Is there a way that we can provide the experimentalist with a kind of a tool to distinguish easily between the operation of HAT versus the operation of proton-coupled electron transfer? I think we can. And there are two ways to distinguish the two relatively clearly. When we look, for example, how the transition state is achieved in hydrogen atom transfer, the crucial feature is that for this hydrogen atom in transit, being transferred from the methane molecule to the accepting O site here, there is a node. There is a node here. In contrast, for the proton-coupled electron transfer, that oxyl site here is a kind of a spectator. All the action takes place here. And it is actually the Lewis acidity of the aluminum side and the Lewis basicity of the bridging oxygen atom here, which controls all the chemistry here. One can also go a step further and can provide the chemist with a diagnostic tool. And that is shown here. When one plots the deformation energy, that means the energy difference when from the reactants towards the transition state, when one plots this energy versus the barrier of the reaction, starting from the encounter complex, there are some clusters given in red where both are by and large identical, plus minus a few percent or so. And some others in which there is a huge difference, in which the deformation energy is much, much higher than the observed activation energy. So there must be some intrinsic stabilization, interaction energy, which distinguishes these clusters from these clusters here. And that is, of course, easily understood. For the conventional HAT transfer, there is practically no kind of interaction energy, orbital energy, electrostatic, Pauli repulsion, and the like, while for proton-coupled electron transfer, it is this interaction energy which stabilizes the transition state. Yeah. So that was my chemistry about CH bond activation of methane. And before closing, I should like to say a few words about a related and yet entirely different chemistry, but again, with a focus on methane. And that is chemistry which I would like to introduce by making reference to a beautiful quotation. When Yves Chauvin received the Nobel Prize, he started his Nobel Prize address with this fine statement: chemistry is marked by magic moments. I fully agree with this kind of statement. What was he referring to? What was Yves Chauvin referring to? He was referring to a reaction which is well known in the chemistry community, the so-called olefin metathesis. This olefin metathesis, as shown here, has also an equivalent in the literature. In Goethe's famous novel, Elective Affinity, die Wahlverwandtschaften, in a Gedankenexperiment describes Goethe the exchange of couples, of partners in couples. Well, there's one couple, has a partner Helmut and Inga, and there's another couple with D and C. And after a while in this Gedankenexperiment of Goethe, the partners find themselves in new arrangement. But as Goethe describes it, that reaction does not take place spontaneously. It requires the presence of a Mittler, a mediator, a catalyst to make the reaction going, because there are barriers involved, both in real life but also in chemistry. Because in chemistry, this process here, the reaction is characterized by a symmetry-forbidden transition state. And that, of course, has the consequence that the barrier is high and the reaction is of no value whatsoever. The yields are low. There are not only two products, there are dozens of products formed. And so the chemistry is, as I mentioned, completely useless. Except, and that was the contribution of Chauvin, except the chemistry is conducted in the presence of a metal carbene. When the metal carbene of this species here is present, out of a sudden this reaction goes like click. And in fact, metathesis processes in a metal-mediated fashion are in the view, I am not a synthetic chemist who anyone takes serious, but in the view of many synthetic chemists, that is one of the most fundamental contributions to the repertoire of chemists in the last 50 years. This kind of metal-mediated olefin metathesis. There are numerous Nobel Prizes given for this kind of chemistry, and also worldwide is an ongoing activity in Germany. Alvis Fürstner or Siegfried Blecher in the audience they did fundamental work, or Peter Shen from the ETH Zurich, he did superb work with regard to the mechanism and the like. So, why are we interested in metal carbene type chemistry? The reason is that small metal carbenes, those metal carbenes which are completely naked, which are electron deficient, which are short of ligands, they are extremely reactive. They are so reactive that it's difficult, if not impossible, to study them properly in solution. And therefore, we decided to go into the gas phase, to do gas phase type experiment with metal carbenes. And there are many, many interesting aspects. I will not go in all of them, except this one here, the chemistry with methane. All the other ones you can read in this accounts article published a few years ago. But here the chemistry of metal carbenes or metal carbides with methane may reveal some interesting aspects. Because it could well be that they are also a way to understand Fischer-Tropsch chemistry better, that is, the oligomerization of methane to form carbon-carbon bonds here. So, there were already in the literature quite a number of studies in which people tried to bring about oligomerization of methane. But the yields were by and large negligible, they were varying, and there were all kinds of problems. But things changed completely when we look at gold carbene, given in red here. Gold carbene at room temperature, when it is brought together with methane, there are just two products formed. A gold ethylene complex, obviously carbon-carbon bond activation has taken place, as well as atomic gold and C2H6. What may be the mechanism? Is that a complicated one? We were quite disappointed. We did really high-level calculation, and it turned out that is freshman type chemistry. There's nothing special about it. Because of a strong relativistic effect, gold is a rather electronegative element. It pulls away electron density from the methylene, makes it even more electropositive. And so this methylene unit can be, as shown here, directly inserted into a CH bond, and then we just fly over that potential surface to form the product. Yeah. More interest, in my view, are not the carbenes, but the carbides. Metal carbides were for the first time reported in 1892 in a Nature article, but then they disappeared. Sleeping beauties in the chemical literature. But in the last 15 years, there's a resurgence. There's much more interest in this kind of chemistry for various reasons here. And now I would like to share with you some recent results on the chemistry of gold and other carbides, diatomic system when they react with methane. And again, based on coupled cluster type calculation, the mechanism we suggest is again trivial. Gold carbide and methane in a barrier-free process, a hydride transfer takes place. A hydride transfer from the methane molecule towards the carbon, and then in a multi-step sequence, everything is inserted to eventually end up with the formation of gold and ethylene. So CH bond activation precedes carbon-carbon bond activation when one is dealing with this kind of carbide system. What happens if you use a cheaper metal like copper carbide? Is it more of the same? Or do we find here perhaps something completely new? Something which might open a venue to entirely new chemistry. When we look at the product distribution, there are some commonalities with the gold carbide, but there are also differences. And the major difference is that copper carbide is at least a factor of 2 or 3 more reactive than is gold carbide. And why is this so? The answer is given in a rather long paper in the journal American Chemical Society. Let me take you through it. When we do calculation, good calculation, for two processes, the stepwise, which I have already mentioned for the gold carbide, where this hydride transfer takes place, insertion takes place, and so on and so forth, that has a barrier which is 30 kilojoules below the entrance, so we can simply fly over it. That also holds true for copper carbide. There's also a stepwise reaction. But in contrast to gold for the copper carbide, there is a new process which I have not yet shown, which I will show in a minute, the so-called concerted one, which is an order of magnitude better suited to bring about this kind of complex chemistry here. And here's the result. In a process in which the two spin states, the singlet and the triplet, merge, and then on the singlet surface of this system here, in one step in the transition state here, everything which is shown here in detail, the simultaneous transfer of two hydrogen, SH minus, a back bending of the newly formed methylene group, a rotation around the carbon-carbon bond which is formed, and then a slippage of the copper from one end to the terminal site here. We do not know if that is true, but that is the only mechanism which can explain so far all the details. All other mechanisms are worse. And if that is true, that would be the most elegant molecular ballet I know of, in which in one step, 4 different elementary processes takes place. A real wonder what nature can do. Yeah. Why is it so? Why is copper so fundamentally different compared with gold? There are 2 reasons. One reason is the gold carbon bond in the carbide is extremely strong, more than 500 kilojoules. And so the barrier for a concerted process is high. On the other hand, the copper carbon bond in the copper carbide is 180 kilojoule lower. So it has a much smaller barrier. So that is one fundamental difference between the behavior of gold versus copper. But there's an even more important aspect. When one teaches chemistry, that is what I have been doing for more than 40 years. Chemical reactivity is usually explained in terms of frontiers orbital. The highest occupied molecular orbital, the HOMO, and the lowest unoccupied orbital, the LUMO. The larger the gap is, the less stabilized is the transition state and the slower the reaction is. And that explains why, for example, atomic carbon does not react at room temperature methane. It takes 800, 900 centigrade, because there is a huge gap between these 2 orbitals here. Upon complexation of a carbon atom with copper, as shown in the middle part here, what we see is that is pulled down, and the barrier is also pulled down. But another important difference between copper and gold is, based on the beta type analysis, the bond in gold carbide, is mostly covalent, while the bond in the copper carbide is mostly, if not exclusively, of electrostatic nature. There's practically no covalency in it. Well, if that is true, why not, as shown here in the lower part, replacing the copper just by a point charge? Believe it or not, the same happens. You pull down the LUMO. And in a very, very detailed study, that is what Dr. Lee, a postdoctoral, did in my group, he was able to show that, yes, indeed, the barrier for this concerted process depends crucially on the charge, on the magnitude of the charge, and the orientation towards this carbon atom here. If the charge on the other side, the barrier goes up, But if the charge is here, and the closer it gets, the positive charge to the carbon atom here, the lower is the barrier. With other words, oriented electric fields can actually mimic part of what is so far assigned only to transition metals. And in the review article, we have also analyzed that a bit more in detail. And one of the co-authors, my friend Saston Scheik from the Hebrew University, he likes to talk about this kind of oriented electric field effect as a smart reagent of the future. Maybe he is right, we shall see. Not today. So the very last chemical slide is shown here. How are carbon-carbon bonds made in the interstellar space? There's methane. There's also a species like this one here, protonated carbon, that is properly characterized. And from laboratory experiment, we know for sure, when Hc plus come together with methane, that is the most perfect click reaction, better than anything what Sharp and others have invented. In a practically barrier-free process, one product is formed, and that is C2H3 and other interstellar species. And it was Eli Lee who did the computational work, and we see it here. There's a gain of more than 600 kilojoules when they come together and they kick off H2 also spontaneously, and this interstellar species C2H3 is formed. When we entered the field of organometallic gas phase chemistry in 1985, that was our first paper in that field. At that time, there were already numerous studies done in laboratories in the United States. And in a leading article in the accounts, which turned out to become the Bible of gas phase organometallic chemistry, Peter Armentrout from Berkeley and Jack Beecham from the Caltech published this article, and you can read it by yourself, how frustrating the situation after all still was. One knows so much, and yet we have so many questions which remained unanswered. Even the most simple one, the detailed understanding of the H activation, was at that time not possible. However, in the last 30 years, due to the enormous improvement on the experimental side with all these superb techniques, of which I have mentioned only one today or two today, and also much better codes to address questions on the computational side, which were impossible to address 30, 40 years ago. We now really know in quite some details, what matters to bring about carbene formation, or this two-state reactivity scenario, this really fundamentally new process, when thermal reaction different spin states are involved, or the role of high spin density in simple CH bond activation here. All this more recent observations that CH bond activation and carbon-carbon coupling can also be affected in a predictable way. I started the Gerhard Ertl lecture by raising the question, what could be simpler? What could be simpler than activating of methane? But when we look at the mechanistic landscape, it is rather complex. It is dizzyingly complex. We have practically everything you can think of. We have proton-coupled electron transfer, simple hydrogen atom transfer, hydride transfer, competition, the synchronous activation of 2 CH bond here. Is this picture complete? Do we now know everything? I am not sure. I am not really sure. I think we are better if we remember and if we remind ourselves on this parable of these 6 men who went to identify an elephant, blind men, just by touching different parts. You can read it by yourself. The 6 men of Hindustan, to learning much inclined, who went to see the elephant, so all of them were blind. That each by observation, by touching, might satisfy his mind. So each was partly in the right, and all were in the wrong, because the total is more than the sum of its component. We must not forget this. And that brings me to the last 4 slides. When Gerhard Ertl yesterday and 16 years ago received the Nobel Prize in his absolutely fantastic lecture in Stockholm, he talked about the relationship of the small and the complex, of the simple and the complex. And he concluded, so to speak, his life work in surface chemistry in one picture, in one sentence, saying, ein Baguette ist mehr als die Summe seiner Krümel. The baguette is more than the sum of its crumbs. How true. We must not forget it. When Goethe, who was already mentioned today on several occasions, when Goethe was asked how to explain his enormous broad interest, not only in literature, but also in natural sciences, in politics, and so on and so forth, he had a simple answer. My work is that of collective efforts. It simply carries my name, Goethe, in a way that also holds true for what I have been doing. Everything I have mentioned today and all the many papers we have published in the lectures I have given, all that would not have been possible without the experimental, the intellectual contribution, the criticism and the encouragement of staff members, of students, of postdocs, of fellow colleagues from all over the world. So if there's any gratitude, any thanks, the thanks must go to these people. Before concluding and joining you for a glass of champagne or whatever will be available, let me conclude on a personal note. In my more than 50 years in academia, Andrea Beck, my former secretary, is in the audience. She knows the exact numbers. I have given close to 1,100 invited and named lectures. You mentioned that. Not to mention the various speeches in my capacity as Humboldt president, or the 5,000 classes at my alma mater, which I shared with students. So from a scientific point of view, I have nothing more to say. Nothing more to say, because it also holds true what the Ecclesiastes once mentioned. To everything, there's a time. Jedes Ding hat seine Zeit. But I have one more thing to say, that is, danke, vielen Dank. Thank you very much. It takes me.
So thank you. Is this microphone? So thank you very much for this wonderful, enlightening talk, giving us insight and an overview to the elephant.
Yeah.
And we now will, following the proposal of Helmut Schwarz, we will postpone the discussion to the reception. But because Gerhard Ertl cannot be with us, we want to give the word to Gerhard Ertl, and maybe he wants to ask a question and make a comment. So please, Gerhard.
Can you understand me?
Yeah.
Dear Helmut, I have attended for almost 4 decades exciting lectures by yours, and I think today this was a masterpiece of this kind of lectures. I was always impressed by your deep insight into the mechanisms of chemical transformations and the originality of your approach. And this lecture showed again how complicated chemistry can be. We can only return to Goethe, who also once said in his conversations with Eckermann, "There's no greater joyous than the study of nature." There's keine größere Freude als das Studium der Natur. Thank you very much for this gift.
Danke, Gerhard. Vielen Dank.
And we will now come to the next step of this ceremony. And I will award you a certificate. And I first read it. So for each award, there should be a certificate. So the Gerhard Ertl Lecture 2023 is awarded by the Berlin Universities, the Fritz-Haber-Institut of the Max-Planck Society, and BASF to Professor Dr. Helmut Schwarz, Technical University of Berlin. Berlin, 11th December 2023, and signed. So please.
Wunderbar, danke. Freut mich sehr herzlich. Danke. Jetzt will ich das noch aufmachen, ja. So.
And
Du musst den auch dazu, nicht wahr?
Bilder. And then there is also a book which you might already have, but
No,
belongs
but
to
I've
the
heard
Gerhard
about
Ertl Lecture Award,
ja.
which is
Ja.
Lebenswerke in der Chemie, Gerhard Ertl,
Ja.
Mein Leben mit der Wissenschaft.
Großartig,
So,
danke.
please, thank you. And finally, there is also flowers. And then we have to, you know, and now we have to give an applause to Helmut Schwarz, and we have to help him. And maybe we like this halten oder so.
Ja, ich war da, ich habe ja gute Hilfe. Ja. Ja, ja. Ja, gut. Danke.
So thank you very much. Congratulations once again for everything, for the wonderful talk, for your work. And we are now closing this seminar and have fun at the reception. So please follow us to the Wintergarten, and there is time to discuss with the award and maybe ask questions.
Sure.
Thank you.